So let's talk about bonds in this video. So let's start off talking about covalent bonds. So covalent bonds, a couple of things to really note is they're the strongest bond. And this is really where two or more of the nonmetals share. So we're talking about sharing of electrons. Now, in some cases, the two atoms can share one, which we call a single bond, or two, which is a double bond, or three, which is a triple bond. And we can see some examples of that here. Here we can see in this methane, we can see a carbon is attached to individual hydrogens, and we're just looking at the sharing of just one electron. And thus we represent it with the single. Here we can see O2, and in this case, we can see that we actually have two that are being shared. So it's represented by the double bond, and here there's three, and you can see that we represent it by the three lines. Okay, so covalent bonds, as I said, they're the strongest, and they could either be a single, a double, or a triple. Now, the protons attract electrons, and this is a concept of electronegativity. So in elements, electronegativity increases from the bottom left to the upper right of the periodic table. And for example, fluorine is the most electronegative of the elements. And electronegative elements strongly attract electrons, and they pull them away from less electronegative elements. So once we have this sharing of electrons, there's a couple major cases, and one is that group of non-polar. So when I'm looking at non-polar covalent bonds, so these are two nonmetals in the molecule with similar or identical electronegativities. And the key word is that they share the electrons equally. So both of them will share the extra electrons in a very equal manner. Now, nonpolar molecules occur in three situations, and the atoms are sharing the electrons are the same element. The arrangement of the atoms makes one atom unable to pull more strongly than another, and that's if they don't have equal, but if one pulls, etc., it can make up for the deficit. Or the bond is between carbon and hydrogen. And of course, this is a very important case because when we really start to look at organic molecules, the backbone is carbon. And carbon really likes to hook up with it. It's with other carbons and also with hydrogens. And this becomes part of what we often refer to as carbon backbones. And carbon is a central player in organic molecules. So when I'm talking about, let's have a look at some of this. So I'm talking nonpolar covalent. Here's an example we could look at. We can look at hydrogen molecules. And in this case, they both equally share. So each one of these pretty well gets half the time it kind of shares, it has that, right? So the electrons spend equal time around the two hydrogen atoms. Now remember, the charge on an electron is negative, right? So if an electron was spending way more time hanging out with one than the other, then that would sort of tend to make that end a bit more negative, but that's not the case when we're looking at nonpolar covalent because the sharing is equal. So over a unit of time, the negative electron is shared equally. Okay, then we have polar covalent. And polar covalent bonds, this is usually when we have nonmetals with different electronegativities, and they share the electrons unequally, and this forms the polar molecules. So atoms with a higher electronegativity become partially negative because it tends to, it almost hogs that electron. It goes, okay, it's an unequal sharing. That more time that electron's hanging out with that atom with a higher electronegativity. And remember, an electron has a negative charge, and therefore that atom would seem like it has more of a negative sort of atmosphere around it. The atom with lower electronegativity becomes partially positive because the electron is pulled to the other one. And what we tend to see is dipoles, which are polar molecules with partially positive and partially negative ends. And here's a classic case of a polar covalent bond. And this is two hydrogens and an oxygen, so not surprisingly, H2O. Almost everyone on the planet knows that is a water molecule. Now what we see happen in this case, it's a polar covalent, so the electron is not equally shared in this case, that the electron tends to spend more time down at this end. As a result, what we see is when we look at the overall molecule, that since the electron tends to spend more time around the oxygen, that this whole structure here has what is functionally more of a negative end and positive ends. Now, this plays an important role because there's another type of bond we can talk about. When this water molecule interacts with this one, of course, the positive and the negative are attracted to each other. And this is the concept of hydrogen bonds. So this is the weak attractions between partially positive ends of one dipole and partially negative ends of another dipole interacting. Now, of course, this is very important in the world of biology because this is what keeps water molecules together. So water has a fair amount of cohesion to it, and it is also responsible for things such as surface tension. Now, you're wondering, okay, this is great, but how does this work into the world of biology? We're going to see the surface tension when we get to the alveoli in the respiratory system is a very important consideration in the functioning of those alveoli, but we're going to leave that story for down the road. Now, polar water molecules are more strongly attracted to one another than to nonpolar air surface molecules. And that's what allows for this creation of a surface tension. So we can see here the hydrogen bonding between the water molecules creates surface tension and causes the blood to form droplets because these molecules, because blood is mostly water, are much more interested in being attracted to each other than to the surrounding air molecules. So they'll pull against each other and you get that droplet forming. Okay, we're going to leave it there and we'll pick up a bit more about bonding in the next video.